I will be doing problem 5 from assignment 4. The problem states, assume that you have a processor with the following specifications. There are 5 pipelining stages as seen in the lecture notes. The branch comparison is done at the second stage, and the program counter is updated at the third stage. For the jump instruction, the counter is also updated at the third stage. There is no branch prediction, speculative execution, or delayed branches. You can't fetch the instruction until the branch comparison is done, and then also register write and register read can happen in the same clock cycle. So the problem has this line of MIPS assembly code. So what this code is doing is it has T0 set to 10, S0 we don't know the value of, and it compares the value of S0 to 10. If it's less than 10, T1 is set to 1, and then it goes to the branch stage. It'll branch if T1 is equal to 0. It finishes the program. If not, then it goes to the next step. In the next step, sum is incremented by 1, and then after that, the program counter is incremented by 1, and then it does a jump back through the loop to keep going until S0 is equal to 10.
So part A says, assume that the data path does not contain the forwarding logic. Using the diagram below, show the stalls needed for a single iteration of the loop, and also assume that the branch is not taken. So for these kind of problems, the first thing you should do is check to see for any dependencies. So we see that register T1 in the branch equal instruction depends on the result of the register T1 in the set less than instruction. So we know that we will probably need at least one stall. So first we go through the first instruction, the set less than. We don't see any previous instructions, so we can assume that no stalls are needed, so we don't put any stalls there. For the second instruction, however, we do have to wait for register T1 to be updated since there is no forwarding, and so we're going to need a stall so that the register files are written to and read from in the same clock cycle. So we're going to put the rest of the steps here, and we're going to need a total of 2 stalls. For the next instruction, we know that the branch equal does not update the program counter until the third stage, and we can't do the next instruction until after the program counter is updated. So if it's updated to the third stage, this next instruction can't start until after the third stage, which would be our ALU stage. So this next instruction can't start until right here. So we're going to have instruction memory, register, the ALU here, data memory, register again. I'll go ahead and draw some lines to make this a little more clear. Let me see if that's enough. Okay. So for the next, so that one we're going to need, I'm sorry, not there. We're going to need 1, 2 more stalls. So for the next instruction, we see no dependencies between the add instruction and any other instruction, so we don't need any stalls after that, so that can start in immediately next clock cycle. So that would be instruction memory, register file, ALU, data memory, and register file again. For the next instruction, of course, jump is not going to need any dependencies on previous instructions, so it can start on the next clock cycle. So no stalls needed once again. Data memory, register. Okay, now for the set less than, we know that the jump does not update the program counter until the third stage, like branch. So we have to wait until the fourth stage again to start the set less than instruction. Oh, we need one more line to finish off everything. Oh, sorry about that. I messed up right here. This needs to be register, data memory, and register again. So we need 2 more stalls here and here. So that shows the total amount of cycles needed. This is a diagram showing how all of this code will be executed with all the stalls that need to be implemented. So with this, we see that we need 1, 2, 3, 4, 5, 6 total stalls. So for part B, it says assume that the data path does contain the forwarding logic, and then using the diagram below showing the forwarding and stalls needed for a single iteration of the loop, and assume that the branch is not taken. So this one is very similar to the part A. The only difference is that now we have the forwarding logic. Because of this, we see that the dependency is not a problem now between the branch equal instruction and the set less than instruction, because if we start the branch instruction immediately after in the next clock cycle, we see that the data from the first ALU can be forwarded into the ALU for the branch equals instruction. So there's no stalls needed for that instruction. However, the branch equals does not update the program counter until the 3rd stage, and that doesn't change with forwarding. So we do still need those 2 stalls after the branch equals stage to allow the program counter to be updated before we can continue to this add instruction here. Once again, let me make this a little more clear. For the next instruction, just like last time, there's no stalls needed as there's no dependencies. So that one can stay the same. Oh, I'm sorry, data memory, register, data memory, register. The good thing with this problem is there's no need to access any memory, so we don't have to worry for any memory to be updated or to pull any or to read any information from the memory, so no stall is needed for that. For the jump instruction, again, there's no dependency, so it can start in immediately next clock cycle. And then again, this isn't updated until the ALU stage, so the next instruction can't start till after the ALU stage of the jump instruction. So this will go here, 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 oh, one more, and here. So we need 2 stalls here to wait for the program counter to be updated. So in this one with forwarding, we see that we only need 1, 2, 3, 4 total stalls. So we see that with forwarding, it is more efficient as we don't need as many stalls. So for part C, we're told to consider the following program that includes the loop described above, and then assuming that the forwarding logic exists, as in part B, how many cycles are required for the pipelined MIPS processor described above to execute all of the instructions of the program. So we see that these lines of code are exactly the same as before, and these 3 are the new that are added. The only difference is now we have a dependency for register T0 in the set less than instruction to register T0 of the add-I instruction, but since forwarding logic exists, we shouldn't need any stalls, so it can be ran immediately after the add-I instruction. So we can go through and count the amount of cycles that are needed for each instruction. So we see for the first one, we're going to start in the first cycle, and the next instruction can start in the cycle immediately following, with the last one on the next instruction after that. And since there's no stalls needed, we can start right away on the loop. So we see the loop will have 1 clock cycle here, For the branch equals instruction, however, we know that we need 2 stalls after the instruction, so there will be a total of 3 cycles needed. For the add instruction, we will need one clock cycle. For the next one, we'll need another clock cycle. And then for jump, as in the branch equal, we'll also need 2 stalls, so we'll need a total of 3 clock cycles. So for the first part of the first section, we see that we need 3 total clock cycles. For the second part, we see that we need 9 total clock cycles. And since T0 is set to 10 and S0 is set to 0, we know that we're going to run through this program from when it starts 0 till it goes to 9. You're going to run through the entire loop. So we're going to need 9 clock cycles 10 times. And then on the last time it goes through, when S0 is actually 10, it'll have 1 cycle here. But then for the branch equals stage, you're going to need to finish out the entire instruction, as it's the last instruction that we will need. So it'll be a total of 5 instead of 3. And then that's when we finish. So we have a total of 3 plus 9 times 10, which is 90. Plus 1 plus 5. So using your calculator, you'll see that you need a total of 99 clock cycles. That concludes problem number 5 of assignment 4. Thank you very much.